Jeff Deems is a research scientist at the University of Colorado at Boulder, where he works with the National Snow and Ice Data Center. And his presentation is about laser mapping of snow depth in avalanche terrain, snow variability, and operational support.
Good afternoon. Thanks, Forrest and Scott, for the invite. Really appreciate being back out here in Seattle. Excuse me, there we go. And nice of you guys to arrange some rain for me as well. That's awesome. We're going to talk to you about using lasers to map snow depth, which is a pretty cool new application of this technology and has really given us new insights into how snowpack and snow accumulation varies across the landscape, and with some pretty ready applications for avalanche control, operations, and planning. A whole bunch of folks from various affiliations have contributed to this, particularly funding support from American Avalanche Association and from the Transportation Avalanche Research Pool, which is a consortium of Western departments of transportation and facilitating research into avalanche problems. Variability in snow depth and new snow depth is contributes a lot to our ability to understand snow stability and therefore assess it and make decisions, whether it's in the backcountry or in an operational setting. Some early work done trying to quantify the effects or the presence and effects of spatial variability in snow properties. A couple examples here. Carl Birkeland, for his PhD work, built a digital resistograph, which is basically just a probe that measures the resistance of the snow in profile. Did 500 measurements across a slope and plotted that variability. And he found that the total snow depth was correlated with the snow resistance, and resistance being an index of snow strength. Cam Campbell, back in about 2005, dug extensive rush block arrays, and he tallied up how much snow he moved. It was a ridiculous amount of work, but this graphic in the lower right here, each of those numbers represents a single rush block score across a slope, and you can see the variability in that index of stability, where some areas are quite strong, 5s and 6s, and there's a couple of pockets that are 2s and 3s on the adjacent on the same slope. And he found that the slab thickness, so the slab above the weak layer, was correlated with that rush block score. So some excellent early work detailing exactly some of the problems associated with individual measurements on a slope and with finding a representative location. Knowledge of the spatial distribution of snow is also of importance for avalanche mitigation activities, control planning, and operational considerations. Whether you're planning supporting structures like you see a lot of over in the Alps or on a particular path above Jackson Hole, or plotting locations of GASX exploders, or whether you're targeting avalanche rounds, knowing where the snow accumulates and where it has accumulated is an important consideration for locating those structures or locating your launcher round. Conventional methods of figuring out where the snow exists on the landscape rely a lot on expert knowledge, so an understanding developed over a long period of time about how this processes of snow accumulation and wind redistribution work with the terrain and vegetation, along with a local familiarity of the terrain. And this is an opportunity and has been seen as an opportunity in recent years for using techniques such as mapping with laser scanners or LIDAR to assist both from the planning perspective as well as for operational avalanche control activities. And so really shifting a mindset from imagining, based on your experience, what the snow distribution looks like, to having a graphic that looks like this that can show you at very high resolution what the snow depth or the snow depth change from the previous scan looks like. So I'm going to show you how we make these maps and some ways that we're using those. Libby, you can click on that gray thing and that'll start playing. So there's several different ways that we can collect LIDAR data from airborne drones or terrestrial laser scanners. Basically, it's a time of flight measurement. It times how long the laser pulse takes to go from the instrument to the target and back. Because we know the speed of light, we can turn that into a range. Coupled with a GPS system, we can then locate each one of those points in space very precisely. And so the basic product is a high-resolution elevation data set. We can make two or multiple measurements and subtract the difference between them in the vertical direction to get a total snow depth or a change in snow depth from a previous snow surface scan. And then that individual point cloud is then tagged with these depth measurements, and we can do colored visualizations like this. Dom here is looking at one of the scanners that we use. So these are pretty conventional survey instruments that we're tasking for this purpose. Started a partnership a couple years ago with Arapahoe Basin in central Colorado. A Basin is right near the Continental Divide, pretty high elevation. The base area is 10.8 and the top is 13,000 feet. We've got 3 different areas that we scan at A Basin: the East Wall, which has been in open operation since 1970, Montezuma Bowl, which was added to the ski area in 2008, and then as well an area called the Steep Gullies, which is part of an expansion that is ongoing currently there. So 3 different terrain types, 3 different avalanche problems, and importantly, 3 different levels of institutional experience with the avalanche problems in these terrain elements. So we've been scanning all of these for a number of years and looking for ways to both characterize what happens there as well as look for opportunities to engage these data with the operational activities. If you'll play this one for me as well. This is Montezuma Bowl, and there's a couple different colors that'll show up. This is total snow depth from 0 up to 4 meters, and you can really start to see a lot of the high resolution patterns, and then when it changes, in this case, that's change in snow depth from -2 in blues to +2 meters in reds. You can really see a lot of the high variability in the slab thickness. In this case, this is a change in snow depth before and after a storm. We've got a couple of avalanches in there that were controlled by hand charges, and we can do things like measure the crown width and depth. We can also see a lot of information about the bed surface that it ran on, and a little bit of new snow accumulation in there as well. This particular slab broke just at this terrain rollover, which is not unexpected, but we can see where it tapers out into this lower snow depth environment. Back to the total depth, we can see some really interesting patterns down these gullies, part of which is wind loading, part of it is sloughing that accumulates in there. You can also see a bunch of bomb craters. There's a ski patroller right there. And there's a control rope right there, so we can test if they've got enough tension on the lines. So really interesting patterns that we can start to look at there, look at different accumulation features, and also log where the control activities have taken place. We can spot each of the bomb craters. We can track all the ski cuts. You can see a bunch of the ski cuts up in here. We'll play this one as well. This is Montezuma Bowl again later the same year in 2014. In this case, mostly what we're looking at here is change in snow depth and a lot of negative colors here. And as we zoom in, you can see why. You can see a lot of the moguls. This half of the bowl was open to the public, and we can actually see how much skier compaction was occurring across this slope. Skier compaction being, of course, a really valuable tool in ski area operations to stabilize existing snow on the hill. If we move across the control line to the closed terrain, you can actually see some decreases in snow depth here with also melt runnels. This was due to actually bomb debris, you can see here in this image, absorbing extra sunlight and actually melting the snow in those locations. Air temperatures were never above freezing during this period, so that was all due to extra solar absorption from that bomb debris. If we go back over to the same crown line and we actually draw a profile across it and look at the two different scans, we can see that from the 17th to the 23rd, the slab has compacted a bit and that crown face is actually tipped over a little bit downhill from snow creep. So we can actually measure all of this stuff with this tool, which is pretty cool. Move over to the east wall, 1st of February 2014. Yeah, go ahead and play that. If you haven't been able to tell already, Arapahoe Basin is a high elevation continental wind affected snowpack. Here's one accumulation event that actually is reasonably uniform on this terrain. We can see here mostly about a meter. And then one avalanche round took out all of this, this slide, and we can zoom in and look at some interesting features in this avalanche. A lot of pocking in the bed surface, indicating some differential scouring down into the depth hoar. That was the basal weak layer there. Interesting feature here, we can actually see some of the stock wall on this release. Some real extra scouring where this pocket came down and ran over this cliff and really dug in at the base of the cliffs. And then we can do things like map individual slab outlines and debris piles, calculate volumes. We can do some other things like calculate alpha angles at pretty high precision. So there's a number of things we can do to characterize an avalanche or include this information in a digital avalanche atlas as well. That one. So moving beyond sort of a proof of concept and what can we see with this tool, we've started looking for opportunities for operations support. In this case, we showed up on the 4th of March on a day that had an unusual wind pattern. We do usually get southwesterlies for storms in central Colorado, but this southerly component was kind of odd in this particular storm, and it produced a bunch of weird loading. And if you'll hit that movie for me. So we got there in the morning, did a scan, processed the data on site, and then worked with the ski patrol to actually add to their target list for their avalancher. Most everything was fairly well expected in terms of drifts, but there was one pocket there that's covered up by my picture that they said, what the heck is that thing? We've never seen that form there before. They put a launcher round on it and got a good result out of it. Not the hugest avalanche, but it's not one that they would have targeted without seeing these data. One other thing we're doing to ease the communication is working with the original route sheets that they use. So they use these oblique photographs with a bunch of data entry components on that route sheet. We're creating basically the same thing, but using the snow depth change map in place of that oblique photo. So they can look at a perspective on the landscape that they're quite used to looking at, and then actually draw in targets or draw in results, and then we can do that digitally as well. So kind of a cool application there. Another example from this January, strong northwesterly winds with new snow produced kind of the opposite loading pattern. Again, really strong stripes there. Just looking at the terrain and the new snow, it looked like there was a bunch of drifts and wider areas that they wanted to target. So they actually were planning to shoot that afternoon. Again, we processed the data on site, and looking at the data, the drifts weren't as extensive or as deep as it looked like to the naked eye. And the decision was actually made not to shoot that day, which is not as sexy as scan it and shoot it, but it's a pretty important operational consideration to say, okay, well, we're gonna save a little cash on launcher rounds. We're also gonna reduce employee exposure to explosives handling, et cetera. So the ability to supplement the conventional decision-making process and make a decision either way, not just where to shoot, but also not to shoot if that's appropriate. So this was an important, I think, case study there. I mentioned the terrain expansion that A Basin has ongoing. So most of the ski areas over here, they're expanding into this zone with the steep gullies. The steep gullies are below tree line, very complicated terrain, pretty tough avalancher environment, pretty tough hand charge environment. So the plan is to install a bunch of bomb trams to place explosives. Those of you who use bomb trams frequently know that the placement of those tramways can be fairly critical in complex terrain as far as providing opportunities to access multiple targets, especially depending on which way the wind's been blowing or how the particular storm accumulated. So we've been scanning this area now, and we're using, there's some pictures of the steep gullies, and using the laser maps to help refine the placement of those tramways. So here I changed color schemes on you. We're going blue to white with 2 meters being the deepest here. And as we zoom in and kind of tip around, you can get a flavor for some of the complexity of not only the terrain itself, but the loading pattern that exists on it. And how do you design your tramway effectively to target all of these little different pockets, or enable targeting of all these different pockets? So an initial tramway design was achieved just using conventional means. They went out there and looked at the terrain. They said, okay, I think we can access from here. And so I have a better graphic here in a second that may be a little more visible, but these red lines are the original tramway network and towers. The yellow lines are what we came up with after looking at the snow depth maps. We have a whole series of them. It's quite a different network. It's much less complicated, it's much easier to access, and there's a bit less infrastructure required. So there's the original one again in red. You can see all these different towers. There's a couple of lines in particular that required control above them in order to access the tramway. So there was an additional risk element for the people running the routes. And again, there's the new design. And in particular, some of these lines offer access to quite a number of different loading pockets, so that multiple charges could be placed to address to each one of those load elements. Additionally, safe access to the top of all of those that mesh with existing routes over here at the existing ski area boundary. So we're pretty excited about now the opportunity to go forward, install this network, and then be able to test it in future years and use this same tool to start looking at the effectiveness of it. Just over the hill, other side of Loveland Pass, the Department of Transportation has just installed a bunch of GASX exploders to control the Seven Sisters Pass on US 6. That was motivated in part by an avalanche accident a couple of years ago that was quite a serious deal. And now they're interested in figuring out or assessing how well these new exploders are working to control snow buildup and avalanches in the set of paths. So we're using the LIDAR in the same way, scanning pre-storm, post-storm, and then post-control to get that series of loading and then change in snow depth from the avalanche control. Here we go again, 0 to 4 meter scale this time. So I forgot to mask out the trees before making this, but you can get the idea. Usually cross-loading from right to left here, that's west to east. As we zoom in, these yellow dots or pins are the location of the GASX exploders. So there's a number of different path types here. Paths 3 and 4 in particular are fairly confined in little pockets. Here's a control round done in number 4 here. And so you can see that this sort of confined start zone actually serves to focus the explosion fairly well, and we'll see this in the data in a second, that really is very effective. The exploder is very effective at cleaning out the snow in that start zone in particular. We got good results across the board on this scan, or on this control route, and then we were able to do a scan right afterwards. And if we change this to a change in snow depth from pre-control to post-control, you can see quite a lot of snow removed from both number 3 and 4 here, as well as a pretty good result in number 2. So we're using this tool in this manner to assess the effectiveness of individual control applications as well as individual exploders. So this was a pretty successful run across the board. You can see here in number 6 that it didn't quite hit the highway and piled up in a big cone there right at the highway edge. Looking at some individual exploders, here's one down in First Sister. There's a lower one, and it actually malfunctioned early in the season and never fired. You can see the exploder there, and now you don't see it anymore because it got buried. So we can watch this drift build over the season, and this is actually a pretty cool opportunity. Now we see what happens to this drift in the absence of GASX control, and then next year they fixed that thing this summer, and now we can see how that drift evolves when applied, or when the GASX is applied to it regularly. Similar deal of the lower exploder in number 6. In this case, we see an initial result early. It'll go back to it in a second, but we got one little result, and then this drift starts building over the course of the season right below the exploder. So one of the potential impacts or potential operational concerns with a GASX system is if you fire it too frequently, it actually just serves to work harden and pack down the snow that's directly under the exploder, and therefore renders it less effective at communicating that shock wave to the rest of the snowpack around it. I won't say that this is a conclusive result that that's happening here, but there is some pretty good circumstantial evidence there given the location of this drift, like literally directly below the exploder. So that's another thing that we're going to monitor in the coming years as well. So kind of backing up from the operational perspective a little bit and going to more of how do we start to conceptualize and understand and keep a handle on the spatial variability in snow properties. Just by way of example, we can look at this somewhat complicated set of terrain facets and see lots of features that leap out to the naked eye, in particular these drifts up here by the tree line. And you know, we all, anyone who likes to ski or ride powder on whatever tool has developed a sense over time of where the snow is likely to be soft or hard or deeper or shallower. And that can be important because the total snow depth of the snowpack affects many things. This is far from a complete list, but things like bulk temperature gradients and snow metamorphism, whether you get depth or how fast individual layers round, how deep rocks or vegetation are buried, and therefore core shots. New snow variability, so the thickness of the slab affects the load on the weak layer. So this can be highly variable across a single slope, as some of the images have showed you already. Can affect creep rates and therefore natural avalanches. The ease of skier triggering, how deep your turns, whether you can access the weak layer or not with your skis or your board or your snow machine. And therefore snow metamorphism in the near layers as well, and critically face shots. What we're used to doing is trying to understand the physical processes of snowfall and precipitation, wind, speed, direction, fetch, duration, and the energy balance, what the sun and clouds and shadowing from terrain and vegetation are doing to affect the snowpack. And we're trying to build that picture in our mind so that we can make our on-the-fly assessments, whether this is in an operational context where we're trying to put all these data together, or whether this is just us skiing around in the backcountry trying to make the right decisions for our avalanche safety. And it changes with scale. This can be a small change or a big change on a small scale across a slope, or we can be talking about thousands of meters in elevation. Things like wind redistribution are really hard things. We're not out there all the time. And so we don't get to watch dunes creep across the landscape like this and understand what that's doing to the snow layers. And certainly, even if we were watching it in one location like this, we don't know what's going on the next ridge over. Again, we're building this intuitive leap from what we try to understand from the processes. And I think that's where the type of maps that we're able to build with the laser scanner system can really help us out. We can invert the problem and say, okay, here we know what the pattern of snow depth is, or we know what the pattern of new snow depth is, and we can start to back out from that and say, okay, well, what would have caused that? I think we could probably brainstorm some ideas about why this gully in particular has a lot more snow in it than the surrounding ribs of terrain there. This looks like a pretty solid wind drift right there. That's something that we can see with our naked eye, but we don't necessarily see these smaller features around there with our naked eye. In this case, good example of really putting shots everywhere, trying to get that thing to move. So I'm pretty confident that that drift isn't going anywhere. And again, the change in snow depth, knowing what the slab thickness is on top. If your weak layer is on the surface, you get some surface hoar, and we're able to map what the slab thickness is on top of that. It gives us a powerful tool as to understanding why a particular avalanche extent occurred where it did, or how these terrain features behave over time. Possibly also a powerful institutional knowledge transfer tool. You know, you don't have to work at a basin for 20 years to start understanding these patterns. We can use this tool to start bringing the new snow safety team up to speed. So, exciting stuff, and I'm pretty stoked to be able to share it with you guys today. Thanks.
Are there questions for Jeff? Oh, do we have our mic runner? Awesome. I'm sorry, I can't see past the lights. Awesome. Go for it.
Can a laser see layers in the snow?
Yeah, it doesn't penetrate more than about 1 millimeter into the snowpack, so it's just mapping the surface elevation. An emerging product or project working with some folks that do radar remote sensing as well to do that at the same time, and the radar can actually penetrate the snowpack, but it's not as good as resolving the surface as the LIDAR is, so I think it'll be an interesting coupling there.
Do we have sound in the front 2 mics here?
Try it now.
Impressive study. Thank you for the implementation of that. Can you talk at all about the resolution of the system and the implementation? Like how obviously you've got to crunch a lot of data to get to that graphic and that useful point for a patroller, so to speak. Can you talk about how much effort it was to get to that point?
Yeah, good question. I skipped over a lot of the nuts and bolts there. It takes us about, at the settings that we use, takes us about 25 minutes to do a 180 scan, which isn't all that long, I suppose. The resolution can be varied quite a lot. It's an angular resolution. It comes out to be at about 500 meter range. We're getting about 10 centimeter spacing. So we're getting a snow depth every 10 centimeters for much of that terrain. Yeah, the processing takes a while. That's currently the longest or the biggest time chunk. It takes us about an hour and a half to turn a data set around. The biggest component of that is actually registering the pre and post scans together, making sure that they're lined up exactly. In a true operational setting, we would have a fixed emplacement for the scanner, and therefore we know it's in the same spot every time, and that would reduce that turnaround time quite a lot. Working on it.
Your last example had some trees in it, and it seems like that would have been one of the biggest technical challenges because it's noise and it obstructs your view of what's underneath of it. How did you guys deal with that, and were you able to get to a point where it was automatic, or do you have to sort of identify those things manually?
Do you mean registering the trees?
No, like everywhere that you have a tree, you can't see the surface of the snow, right? And it shows up as a thing in your point cloud.
Right.
But it looks like some of your slides, they were masked out and some they weren't.
Yeah, so there's one in particular. There's a big tree shadow on the hill. I forgot to point that out. We can see through trees at range because the portions of the laser shot actually are reflected by the tree and part of it gets through. So we can actually see through a lot of forest. Elements that are close by, it's basically like shining a flashlight around. And so if a big tree is standing right here and I try to shine my flashlight through it, yeah, it's going to mask a lot of what's behind me. So our choice of scan positions, we try to get a good open view. We can't avoid trees at some level, and we can see through a lot of them, but most of the start zones that we're interested in, we choose a location where we can see them really well.
Thank you so much, Jeff.
Thanks.